I'm trying to use two different computers here to present. I don't have a webcam on my main computer. All right.
Just make sure that your face, yeah, that we see your face.
Yes. Okay. Share content. Share screen. Okay. I think that should have come up now.
Yeah.
Okay. Oh,
I see presenters view.
Presenter view. Let me swap that. All right.
Yeah.
So I think 1 o'clock now. So I'll go ahead and get started. So thank you all for coming. This will just be a mock presentation of some of the work that I've done for my candidacy exam. So to begin, I'd like to talk about the function of functional groups. So as chemists, we are intimately familiar with the many roles that functional groups can play. They can dramatically affect the reactivity, physical properties of molecules, and in a way, you can think of them as the colors of a chemist's paint palette. In the same way that an artist would use different hues to produce a beautiful image, we use different functional groups to produce a very unique molecule, or with a molecule with specific properties. So it behooves us to explore all the different colors the same way it would benefit an artist, and not overlook certain functional groups that may be more exotic or out of the way. And one such group that is a bit more niche is the sulfur pentafluoride group, SF5. So we can see here the SF5 group is an octahedral geometry of a centralized sulfur bound to 5 fluorines in a square pyramidal geometry. We have our 90 degrees angle between all the fluorines with these 4 equivalent equatorial fluorines and 1 axial fluorine here. Now, the electronic properties of the sulfur pentafluoride are perhaps the most interesting. We can see that it is sometimes called a super trifluoromethyl group, and that's just due to the increase in the number of fluorines. CF3 has 3 with the 2 extra fluorines. We see that there is some more interesting, more powerful electron withdrawing effects. And this can be determined quantitatively by the Hammett parameters. Essentially, by looking at the acid dissociation constants of benzoic acid or the aniline cation with different substituents, we can determine how the substituent would affect the acidity of the molecule. And in table 1 here, we see that there is a significant increase in the sigma for the para-substituted SF5, 0.68 compared to the 0.53 of trifluoromethyl. The same is true for the para-substituted aniline cation, 0.86 compared to CF3's 0.65. This just meaning that it's a much more powerful electron withdrawing group, as expected. We also have in the bottom here some the inductive and resonance effects. Inductively, SF5 again much more powerful than CF3 in terms of its ability to pull electron density towards itself in a molecule. In terms of the resonance effects, not much of a difference actually between the two. Now, the pKa, which we're all more familiar with, also shows the same story, where we see a much lower pKa for the SF5, almost comparable to the nitro group in terms of its electron withdrawing ability, and the dipole moment of the aryl SF5 here is much stronger or much higher than the dipole moment of the trifluoromethyl toluene. This just meaning that it's able to more polarize bonds more effectively than CF3. Now, in terms of sterics, we see a similar story where the SF5 will be bulkier, and compared to the geometry of the CF3, we see that it is octahedral instead of tetrahedral. It's a larger functional group, so the atomic volume is larger and is also much denser. These atomic volume and density parameters were found for the benzene derivatives of the respective group. Sterically, the SF5 is a little bit smaller than a tert-butyl group to kind of get a comparison there, but much larger than the CF3. So this places the pentafluorosulfonyl group in an interesting position, where it's a highly polarizable, strong electron withdrawer, but also lipophilic, being so bulky. And typically, you don't see this in strongly polarizing groups. The Hansch lipophilicity constant pi can be calculated by observing the equilibrium between water and octanol. And we see here that the SF5 is actually quite lipophilic, similar to tert-butyl group in terms of its lipophilicity. More similar functional groups with more electron withdrawing properties, like the nitro, are nowhere near as lipophilic as SF5. So more very, very strongly electron withdrawing, very lipophilic, and also is quite stable. We can see here that SF5 is resistant to hydrolysis and boiling concentrated sulfuric acid, as well as resistant to hydrolysis in basic conditions as well, stable at both of these conditions. CF3 would not survive these. It would hydrolyze under these conditions. Also thermally quite stable. 7 hours at 400 degrees Celsius, there was a little decomposition. So this is beneficial to the post SF5 installation functionalization that we could do with this molecule. We could put it through the ringer in terms of reductive and oxidative conditions. And you can see here just some reported reactions. I won't go through them all in detail, but you can see that everything from Suzuki coupling to strong oxidizing conditions here to even nitrations and reductions with palladium and carbon. All of these can be, even Grignards, all of these can be accommodated for due to the impressive stability of the SF5 group. So this has opened the doors now for a wide range of applications, but mostly relegated to the pharmaceutical industry. And as I mentioned before, the SF5 is quite lipophilic, so you're able to install a very powerful electron withdrawing group, but not affect the drug's ability to pass through fatty membranes. So it's had great success in pharmaceutical applications, where you see here these anti-malaria drugs at the top. This is called mefloquine. And replacement of CF3 groups with SF5 has allowed this drug to not only maintain its selectivity against the malaria parasite, but also increase its in vivo activity and effectiveness. Now, the other drug here, a similar story. This is unnamed, but it's a triazolopyrimidine inhibitor. It also has improved effectiveness with the SF5. Same story for the agrochemical industry. These herbicides, this one specifically called trifluralin, has improved activity with SF5 functionalization. And SF5 has also found great applications in the optoelectronic field. This one example is just of a liquid crystal that is used in displays. Just due to the increased polarity of the SF5 group, you're able to better increase that dielectric anisotropy, which is the major parameter for liquid crystal display technology. So everything sounds pretty great up until now for the SF5, but what's the catch? And the Achilles heel, you could say, of this group is the synthetic accessibility. Essentially, it's very difficult to make. Historically, SF5 synthesis has suffered from several major drawbacks: low yields, costly and or dangerous reagents, limited substrate scopes, and difficult to handle gas reagents. The initial report that described the synthesis of aryl SF5s was in the 1960s by the Shepard Group. They used diaryl disulfides with 8 equivalents of a very expensive silver fluoride with freon at 130 degrees Celsius to obtain this aryl SF5. 9% yield, very poor yields. Now, no work was done on the, or no major publications were made since this 1960 report for almost 4 decades. And it wasn't until 2000 that the Zen Group reported a new synthetic method. However, it wasn't much of an improvement. Using the explosive xenon fluoride, they could obtain slightly better yields, again using the diaryl disulfide route. The same year, the Philp group proposed the following. They could obtain again a slight improvement in the yields of the SF5. However, it used toxic, highly dangerous fluorine gas. And the substrate scope was only limited to the electron-poor diaryl diphosphenes substituted with the nitro here. So things were looking pretty grim until the last decade, 2012, a landmark, which was a landmark year for SF5 chemistry. The Nikonov Group published a practical and economical 2-step procedure. Now, this really did change the game for SF5 chemistry. Now, the first step in this 2-step procedure was an oxidative fluorination step. Again, we're sticking with the diaryl disulfides. However, as you can see, a large increase in the tolerance for various substituents was reported. However, this did use chlorine gas. Now, the first step, the oxidative fluorination, resulted in this trifluorosulfonyl chloride intermediate in pretty good yields. And then the second step was a chlorine-fluorine exchange, in which a fluorinating reagent, like the cheap zinc fluoride, could be used to furnish the final aryl SF5 product. Some additional improvements were made even recently to this already revolutionary work with the 2019 publication, where the Pitts group further democratized SF5 with the use of the cheap oxidating acid here. So this trichloroisocyanic acid, TCICA, was used instead of chlorine gas. And although high equivalence of the acid was needed, this is produced on an industrial scale. It's actually a cheap pool cleaner. And they could obtain the step 1 product, the tetrafluorosulfonyl chloride, via this route. In addition to this, the Pitts group reported an even further expansion of the functional group tolerance. Not only could various functional groups be installed onto the aromatic diaryl disulfide, but a wide range of heterocycles could also be tolerated. Everything from pyridines, pyrimidines, triazoles, indazoles, quite broad in terms of the functionality of this route with the cheap TCICA. So to summarize kind of the modern developments now on an SF5 synthesis, we have our first step, which is that oxidative fluorination can be done either through the Yamamoto method with chlorine gas or with the TCICA, and that tolerates both aryl and heterocyclic diaryl disulfides to obtain the trifluorosulfonyl chloride. And from there, the step 2 can be done, the CLF exchange can be done in a variety of methods. And these are now the most recently published routes. In fact, just in 2021, a few months ago, the Shibata group here reported the use of silver tetrafluoroborane in order to form the SF5 group here as a step 2. But various, and this is a comprehensive list here, just some of the more popular ones, various second step CLF exchange routes have been reported in recent years. So despite this large recent increase in the accessibility of the SF5 group in terms of its synthetic protocols, we're still kind of lagging behind in terms of finding applications for this very unique and very interesting functional group. And that's where my proposal now comes in, which is the synthesis of SF5 substituted ligands for applications in transition metal catalysis. So my plan here would be to functionalize the popular phosphine ligand motif with the aryl SF5 group. In doing so, I hope to create highly electron-deficient SF5 substituted ligands, which are expected to stabilize lower oxidation states, enhance metal Lewis acidity, and increase selectivity via the steric bulk of the SF5. This should result in very highly active transition metal catalysts for applications in cross-coupling and many other things as well. So essentially, I'm focused now on the ligand acceleration effect, right? Which is the improvement of catalytic performance via the attachment of, or via the modification, you could say, of certain ligands. General concept, as I said, is improving reaction rates in already existing catalytic transformations with the modifications of ligands. And an excellent example of this was the work reported by the Fagnell Group in 2010, where they showed specifically the influence that electron-deficient ligands can have on catalytic reactivity. The S-phos ligand here, based on the popular biaryl Buchwald type phosphine ligand, was synthesized, and the CF3 group, as well as the fluorine and the typical aryl, were made here as ligand 1, 2, and 3. This is increasing in terms of electron deficiency, and they observed for the specific cross-coupling here using palladium as a metal, a dramatic increase in yields and rates proportional to the electron withdrawing ability of the phosphine ligand. We see here that the trifluoromethyl group performed better than the fluorine, which performed better than the hydrogen, which performed better than the very electron-rich cyclohexyl. So, as I've previously established, the SF5 is a more powerful electron withdrawing group. We should see dramatic increases in yields and reaction rates, and even possibly some more electron-deficient cross-couplings, which weren't possible in the past, could now maybe be possible with SF5 functionalization. Now, this idea of electron pore catalysis isn't new. It's actually there's a great review by Pollock, who recently reviewed the role of electron-deficient fluoryl aryl phosphine ligands in homogeneous catalysis, and their conclusion was that the importance of this field is rapidly growing. In fact, there was many catalytic applications for these electron pore ligands, everything from hydroformylation to all these different couplings and so on. And this isn't even a comprehensive list. And in all these reports, they have seen that the more electron pore the ligand, the better the rates of reaction and the yields, and even enantioselectivities in some cases as well. Some of the popular ligands here I've shown. Polyphosphines are popular, as well as monophosphines here as well. Now all these ligands and all these reports, no reports of SF5 functionalized ligands have been made yet. So why is it that electron-deficient phosphines are more effective at this catalysis? And it has to do with well, we can look at specifically the ligand acceleration effect in palladium cross-coupling. For example, if we were to cross-couple an aryl halide with this benzene ring, we can imagine a hypothetical electron-deficient phosphine ligand based on the Buchwald structure. And in the reaction mechanism, we know that we undergo this oxidative addition to form the intermediate here, followed by a substitution of the halide with base to get this carbonate complex shown here. And then we go through a CMD, the transition state, that is the concerted metallation deprotonation. And in this step, we have an interaction between the palladium center and the carbon, the sp2 hybridized carbon of the aryl ring. Simultaneously, the carbonate extracts the hydrogen, and it is in this step that is typically found the barrier, the energy barrier of the catalytic cycle. So stabilization of this transition state is directly proportional to the increase in the rate of the reaction. And electron-poor ligands are excellent at stabilizing this transition state, just due to the affinity that they have with the carbon, or an increase in the bonding strength between the metal, the electron-deficient metal, and the electron-rich carbon center here. So through stabilization of this state, we're able to move on to our reductive elimination step, which is also stabilized by electron-poor ligands. Reducing the metal is hindered by electron-rich phosphines, but the electron-poor phosphines are actually able to undergo reductive elimination much more rapidly. Kind of a small counter, and the reductive elimination step is actually the rate determining step for many reactions. But as much as you win in the reductive elimination, there is a bit of loss in terms of the difficulty in the initial oxidative addition. But that's why it depends on the reaction. But for many reactions, this CMD will be stabilized by electron-poor phosphines, and the reductive elimination as well will be stabilized by the electron-poor ligand. So the route to ligand synthesis, I propose, should first involve the formation of brominated phenyl-sulfur pentafluorides. I propose that we could use bromobenzene as to form this thionyl chloride derivative here, and from this we can then do a reduction to form the thiol, the brominated thiol. Oxidation can then yield the biaryl disulfide, and then through the Pitts protocol, we can then obtain our tetrafluorochlorinated sulfide, and then through a fluorination method, I put the one reported here by Imamoto, but if other secondary steps can work as well, we should be able to obtain our brominated, our parabrominated phenyl sulfur pentafluoride. Also, if needed, we could do a synthesis of the 3-bromo phenyl sulfur pentafluoride. However, we would do this a little bit differently in terms of we would first synthesize the aryl SF5 through the reported procedure, and then, since this is a very, very powerful electron withdrawing group, we can be assured that nucleophilic addition here would proceed quite rapidly at the and selectively at the meta position to give us the meta substituted bromine. However, this wouldn't be as effective as a ligand. I would probably stick with the SF5, but it may have interesting steric properties just having the SF5 on a different substitution. Now, with these brominated compounds in hand, we can then turn to synthesis of the ligand. And for this, I propose a Grignard reaction, which has been reported to work. And from this Grignard reagent, we can then do our electrophilic substitutions onto chlorinated phosphine ligand scaffolds, which are readily available. I've shown here the synthesis of an exemplar monophosphine Buchwald. This is the SFOS ligand, but it could also work for like 1,2-bis diphenylphosphine ethane or diphenylphosphine butane, or sorry, propane, to get these simplified polyphosphine ligands. This could also work for asymmetric, like binap ligands as well. And from the brominated SF5, we could also do an iodation to halogen exchange to get the iodated SF5. And from here, we can do a we can use tert-butyllithium to get our PAR3, like our triaryl phosphine, and that would be done with triethoxyphosphine here under these conditions. So with these ligands in hand, we then hope to first characterize them after post-synthesis. After full characterization, attachment to transition metal catalyst, and then proceed to use them in initially cross-coupling reactions. But as I showed earlier, the large list of potential catalytic applications for electron-poor phosphines, the doors are then wide open for further application and metal exchange and all this stuff. Different transition metals can be used. So, in conclusion, SF5 is a powerful electron withdrawing group that is chemically and thermally stable, bulky, and polar. Recently developed synthetic protocols have dramatically improved accessibility to this exotic group, yet no transition metal catalysis has been attempted. SF5 functionalized phosphine ligands are expected to dramatically increase yields and reaction rates for cross-coupling reactions, and the proposed synthetic route is expected to yield a wide variety of mono and polyphosphine electron-poor ligands suitable for catalysis. And with that, I want to thank you all for attending my the mock presentation here, and open the floor to any questions. Thank you.
Thank you, Josh. It was really good.
Thank you. Thank you.
And I really liked your introduction with this
the
nice painting. Yeah. So guys, should we go slide by slide? I don't have that many comments on the slide, though.
Well, I have.
Okay, let's start.
Okay, yeah, sure.
So like slide 2, maybe.
This one.
Yeah. So like here I would like put those angle arcs a bit closer to the elements.
Okay.
Otherwise, like the first impression was, you know, like in coordination chemistry, they use those arcs to show. Yeah. So might be silly of me, but it was.
No, I get it. Yeah.
So, and then like on some slides, like 4th and 5th slides, yeah. So like
I had a mistake here. I think this chart showed up before I wanted it to. I think.
Oh, yeah. So like my comment is that you put the formula, and I'm pretty sure it's in your proposal, like that log k over k0. So like it would be nice to put some legend, just for those people who like just joined, or not familiar, right? Otherwise, you look at the numbers and you just might be puzzled about
right.
Yeah.
Right.
So
I also have a question about this slide, not like a general question. I think if you are talking about pKa, you might be asked if you about the ways how you can measure pKa for different compounds.
Okay. Yeah.
So maybe read into this.
Yes.
Yeah. So like on slide 5, it's just like could you just elaborate on those pictures, like those 3D diagrams, what they are? Yeah.
Yes. Maybe a scheme description underneath that. Scheme.
Yeah. So like just like what is it?
Like electrostatic potential map. So just kind of talk about like
So it was like calculated, right? Or it was experimentally? Okay.
I think it was calculated, computationally.
So, Anton, are you saying that he needs to add some legend, or just to describe it more deeply?
Because maybe I missed it, but just like what it is, like because you can get those pictures, I guess, by doing X-rays or by like implementing DFTs, but just like the idea what it is would be nice.
I think this one specifically was DFT, but I'll make sure of that, and I will describe it more accurately in a legend or like a comment.
Yeah, and maybe the last question here, those lipophilicity constants.
Yes.
Maybe if there is any formula for it, just because otherwise you said this one is more lipophilic, another one is less lipophilic, and then I look at the numbers, and frankly, I just like
right.
I mean, yeah.
And also you might have a question. Sorry, go ahead.
Yeah. So either like a formula and then you can keep numbers, or you can just like put a scale like A is more lipophilic than B, then C, then D, like something like that. Otherwise, just
I think I'll include the formula. It's a pretty simple formula.
And do you know how it can be measured?
Yeah, the lipophilicity constant. So pi is essentially equal to the negative log of the equilibrium between the substituted phenoxyacetic acid and the difference between the equilibrium of that versus the equilibrium of just the regular phenoxyacetic acid. And as you and this equilibrium is basically being measured in the concentration of the substrate in octanol versus water. So they prepare these compounds in a solution of octanol and water, and as you have more of the compound being dissolved into octanol, you have a higher lipophilicity constant based on just that equilibrium.
Okay, I see. Thanks.
Yeah, you're welcome.
That's good. If anyone else has other questions.
I'm good.
Could you go to 15?
I have 14.
Okay.
So here in the synthesis from the disulfide to the CF4 chloride, right?
Mm-hmm.
What is TFA, first of all?
Trifluoroacetic acid.
Okay, so to have chloride, you have to have a chlorine gas or what? Did you forget to put it there, or?
So the chlorinating reagent here is the trichloroisocyanuric acid, the TCICA.
Oh, okay.
And this should both oxidize and chlorinate the diaryl disulfide.
Okay.
And also, maybe I should include it is catalytic amounts of TFA. It is actually not a reagent there. It's just as a catalyst.
Okay. Does anyone have about typos or anything?
I have 14.
Oh, 14, right. 14.
So you said discussing transition state. You said that energy barrier of exactly like energy barrier of the catalytic cycle. Do we say this? I was thinking that it might be rate limiting step.
Yes.
Because the energy barrier is higher. So you sounded a little bit confused.
I was.
Make sure.
My mind slipped on rate determining step for some reason, and that's exactly what it was. I think I kind of caught it later on, but rate determining step is exactly the transition state here, the concerted metallation deprotonation, and it's about like 12 kilojoules per mole or something. It's stabilized with a very electron withdrawing group compared to just a typical like benzene aryl.
Yeah, and on 15, I forgot, you said that it was nucleophilic addition at the last step.
This one here.
It is electrophilic substitution on 15.
Oh, 15.
The last step.
This is electrophilic.
And it is substitution.
Right. Substitution. Yes, because electrophilic substitution, because bromine is the NBS N-bromosuccinimide is your electrophile, right?
Yeah.
Okay, and then you have an attack from the aryl. Okay, my bad. Thank you. That's a good catch.
No problem. Yeah.
And also, could you go to 7?
7?
Yeah, slide 7.
Yes.
Yeah, those arrows are usually used for retrosynthetic analysis, right? And might be a little bit confusing, I guess. So it seems like first one is obtained from the second one, but it's not like that. You're just saying if you change the substituent to another, it will be better, right?
Yeah.
So maybe change the arrow, or I don't know.
Do you know which arrow I could use, or maybe I could just
I'm not
color
sure.
them? I mean, like that would be.
Which one?
Good. If we just like fill the arrow like with some color like orange or something.
Oh, okay.
Because usually it's like a schematic arrow that is used for retrosynthesis. Yeah, something like that. But if it's colored, I don't know, just like.
Yeah.
Okay.
Especially if there are organic people in your committee, they might be a little bit confused.
Yeah, I think I'll fill in the color. That's good.
Yeah.
So,
That's good.
I'm done with my comments.
Yeah, I think it was
Is there anybody else?
pretty good.
Okay, I have
really
just
good.
general questions. Oh, Alessandra, you can.
Oh yeah, no, I was just gonna say, I think I caught something on the last slide. I think one of the bullet points was just missing a word. What was it? Yet no applications in transition metal catalysis. So the second point.
Yet no applications. Oh, thank you. Very good. Yeah,
And also full stop on the last for the last point.
Oh, I missed that. Thank you.
But like otherwise, it was excellent. So
thanks, Alessandro. Yeah, thank you.
Okay, maybe for just general questions, so maybe which question can ask committee if you have any. Let's go to slide 3, maybe. Yeah, so do you have any idea why the equatorial bond is longer than the axial?
I think it's just the steric crowding of the 4 equivalent fluorines, all closely packed around the sulfur, and then you have that additional freedom of the axial position for it to slightly extend a bit further out.
But the angle is 90.
Yeah, everywhere is 90, right?
Oh,
They're same. If you look at it like 90 degrees, tilt your head, it will be
right. Oh, it'd be the same.
axial.
Oh, okay. Okay. In that case, then it may have something to do with the orbital overlap for that axial.
Yeah, that is true. Orbitals are related.
So
but for the sulfur, it's how is it called?
Hypervalent bonds.
Yeah, those are hypervalent bonds. So
yeah. So I was reading a paper that basically described that there isn't a lot of d orbital presence. There is mostly located on the p orbitals for this structure, and I think is actually they described kind of an ionic structure for it, just because there didn't seem to be like true hypervalency going on here. Essentially, it was a sulfur 2, and then 2 of the fluorines were anionic, and then that would be an exchange. But they kind of classified it as a sulfur 2, and then 2 fluorides as like how this would actually look. But I think I do need to be able to explain that hypervalency. Okay.
Yeah. Oh yeah. Slide 5, I think.
Sorry, axial is longer. Okay. Slide 5.
Yes. Why is this group lipophilic? You said it is in this slide. I see it.
Yeah. So it seems to have to do with the bulkiness of the group. It's much larger than the CF3, and that allows it to better interact with bulkier solvents than like a halide would, for example, or something like that.
I just thought that lipophilicity is associated with like London forces, maybe when you have like those long hydrocarbons,
Yeah,
and it's more about active surface, of the group rather than, and like this group is it's polar, right?
Yeah.
Then it should be more or less like hydrophilic, right? How do you call it?
Right. Oh, yeah, but it does
strange.
participate in more LDF than like a nitro group would, just because it's there's more active electron surface because of all the fluorines. So I guess it would.
As you said, it's huge, right? That's why it has more dispersion process with the solvent.
Maybe there are also some interactions like there are like hydrogen bonds. There are also like fluorine bonds. Like I've seen some papers about
halogen
that. So
bond?
maybe that's like it's just like So I guess because you have like 5 fluorines here, like that can actually contribute as well.
Right. Okay.
And also you commented on the stability on slide 6, right? Why is it so stable?
I think that the geometry has a lot to play here. The tetrahedral geometry does open up the CF3 group to to attack from essentially from below, whereas the SF5 is much more protected by this wreath of fluorine atoms. Even though it is more polar and it should be more reactive, theoretically, it is just sterically more protected than CF3.
Okay. Slide.
Yeah, I could just like.
Yeah.
Okay.
Go on.
I just a small question. So you said like those groups might be used for drug design.
Yes.
But what will be the main metabolite? Like if this group decomposes, will it produce any harmful substances? I don't know, something.
Yeah. So based on
is it safe?
It does seem to be safe. It does seem to be safe in terms of toxicology. I think the LD50 is like 4,000 grams per kilogram. Wait, sorry, 400 grams. Sorry, 4,000. So 4 grams. Yeah, 4,000 micrograms. Per kilogram.
For which?
For the aryl SF5. So just a benzene substituted with SF5 like this. It was I think it was 4 grams because it was 4 grams per kilogram, which is very high for like a it's a very safe compound. Also things like the AMES test, which is just like a general test for toxicity, was passed, and it actually, funny enough, it smells like sweet. I don't know, that just some random fact I saw, but most sulfur compounds are terrible, but this one is actually kind of seems to be the nicer of the sulfur compounds in terms of toxicity and all that. Yeah. But the main metabolite, I don't know. I don't know. Yeah, I should look that up. Of what would
just try to maybe analyze what might like we have like acidic and like like media. So just I don't know, just like a rather rough gas would suffice, I guess.
Okay. Like which enzyme or something I can mention.
Not even like enzyme, but like if that just if you look at the chemistry of those simple sulfur fluorides species, like oxidation or other like types of reactions, just to see what will be done. Just like small, very simple products, right?
Okay.
Because sometimes in the drugs, you can get. I know that like aspartame, for example, produces methanol as a metabolite. So just something simple, but then we know that toxicity of methanol is much higher than the the original compounds. I mean, it's related, but
all right. So it would be like a harmful product from after metabolism.
So just to make sure,
yeah. That's good. Thank you.
I usually seen.
Oh yeah, about the catalytic application. You say, as expected, it will stabilize low oxidation states, and CMD mechanism will be easier, right? So my question is, won't it be too electron withdrawing for oxidative addition step? What do you think?
I think it might. It would inhibit oxidative addition, electron withdrawing nature of the phosphine. I do recognize that. But it seems that in a lot of the calculations people have done, The reductive elimination and also this transition state, the CMD, are really the barriers to catalytic turnover. So even though it may increase the barrier of the oxidative addition, the trade-off for reductive elimination benefits and CMD benefits should maybe outweigh that, and that's why we see like ligand acceleration effects in like these cross couplings, but it won't be a general thing for all reactions, for sure. I've seen some reactions that do worse with electron poor phosphines, and that's just because their oxidative additions happen to be closer to being a barrier, and the trade-off isn't worth it for those specific reactions. Yeah.
Okay. And about the synthesis of the ligand later on 16, I think. Yes. Yeah. I didn't understand the last step. So you used terbutyl lithium to prepare lithium reagent, right? Or what?
Yeah, I would prepare lithium reagent of the SF5 there, substituting the iodine. And then this would then do a nucleophilic attack on the phosphorus 3 times to get the fully arylated.
Yeah, I thought if you add, maybe I'm wrong, if you add terbutyl lithium to the aryl halide, won't lithium iodide just precipitate and or not? Oh no, it's a sort of a substitution, right?
Yeah, it'd be a yeah, I think it'd be a substitution. Lithium iodide.
Yeah, I don't know. Oh yeah, it will be a substitution because aryl lithium reagent is more stable than the butyl lithium, right?
Yes, yeah, right, yeah, it stabilizes that negative charge better on the aryl, and then you'd be able to do substitution.
Just forgot my organic chemistry.
No, but that was good. I had to follow you there as well. That's good to keep in mind how it actually works, that mechanism. Yeah.
Why do you need 2 equivalents of terbutyl lithium?
They just reported that in literature. I followed it, but I think maybe I don't know if it needs. I don't know if it's necessarily that like equivalent to sacrificed or anything. I think they just found higher yields with 2 equivalents. But I don't think it's actually like a chemical necessity to have 2.
Maybe it's better to check with the paper. Maybe they somehow explain it.
That's good. Thank you. 16.
Okay.
Anton, about your question, I think they just quench it.
Yeah, but then you'll quench your salt as well, right? Like phenyl lithium.
No.
Post.
After the reaction is
done.
Yeah. So I mean, if you have sorry.
Yeah, terbutyl lithium will also react with phosphorus. Phosphine, right?
Yeah. So it should be like either stoichiometric or some logic behind it.
I think I'll look up the details on this. So like a similar phosphine exchange exchange there, substitution.
They may ask about that, so be prepared.
Yeah, that's good. It's a good question. It's a good question to ask.
Is there any other questions?
I have a question.
Yes.
So I think you have chosen a reaction that you're going to try first, right? The palladium catalyzed. But have you commented on the substrate scope that you are going to try?
I haven't I did in my report, but for here I would say similar to at least initially I would want to try cross couplings. So between maybe electron-deficient aryls and aryl halides, I wanted to try cross coupling there, just because there's still room for improvement in terms of yield and reaction rates in those experiments. But
if you discussed it in the writing part, so that's fine. I was just thinking that you might have missed it.
I could include it. I was just running out of time when I did it.
No,
but
I think that's enough.
Okay, just like maybe one catalytic reaction as like one thing to try, maybe.
Yeah.
Okay. Yeah, because I kind of felt that too. Like I was just talking a lot at the end instead of actually including like a description of like what would be a good catalytic application to attempt.
But if they should have read everything, so don't worry.
That's true. Yeah.
Mm-hmm.
Okay.
Okay.
Any other questions, guys? In general,
No,
or
I'm
critique
good.
or anything? Yeah.
It
Thank
was
you,
really
everybody.
good. Good luck.
Thank you. Yeah, thanks. I'm really worried about these questions, but yeah, I've been. We'll see how they
just
go.
read the theory a little bit.
Yes. Yeah. Good. All right, everybody.
Okay, good luck.
Yeah,
Thank
good
you.
luck with your exam.
Thank you, everybody. Thanks.
Yeah, you'll be fine.
I hope so. Yeah. We'll
Yeah,
see you
slides
all.
were very good. So just read a little bit about theory and should be good.
Okay. Good to hear. Good to hear. All right,
Is it
everybody
on
else?
Monday or when?
It's Monday at 1 p.m.
Yeah.
Okay.
Good luck. Fingers crossed.
Fingers crossed.
Yeah.
Yeah.
Okay, everybody, have a great day. Thanks for coming and
too.
spending time with me here.
Yeah.
All right, take
Bye.
care. Bye.
Great job. Bye.
Thank you. Thank you.